Recording. I know, right? Oh, and we have 36 participants online. Damn. Hello, welcome everyone. Hopefully the sound is good. Chat. Control H. What is happening? One moment. Okay, we have sound. Cool, perfect. Also, my screen is getting recorded. Yeah, perfect. Okay. All right. So here's the plan for today. We have until 7:30. We will go first over the example exam. Then I will answer your questions for maybe an hour, and after that, we will try to think of general questions for what might they possibly ask on the exam. I do have some ideas, and then we're going to try to answer them. Okay. So first of all, did you guys manage to complete the exam, or are you starting here with? Okay, cool. Right. So let me just switch to my board. Thank you. Okay, I'm just going to explain it here. Okay, so yeah, we're going to start with the exam right now. The first question is determine the type of inductive bias of linear regression. The inductive bias is, well, for different machine learning techniques, it's something that you assume. That you assume of the machine learning technique, and this answer, well, is very simple if you do know what inductive bias is. And the inductive bias of, well, in this case, linear regression is well, very simply, you assume that there's a correlation between the input and the output which you input in the model. You assume that there's some impact that your inputs, for example, if you want to predict somebody's salary, right? Some of the inputs that you might want to know is, how old he is, what's his position in the company, for which company he works for, maybe his IQ, the prediction of his success. What you don't want to know is how much cheese costs in Sweden at that point in time, because that tells you nothing about that particular person, right? And this is something that you assume. You just explicitly tell it, okay, I think these features have an impact, right? And well, all those features do have an impact. Yeah, like inductive bias is just something that, a term that you have to learn and that you will never use outside of this course. But the question 2 is more interesting because it's a trick question. I did it last year. And well, they want you to provide a decision list. And as you might remember, a decision list is, well, here. Mm-hmm. I actually don't know the second type of inductive bias. Inductive bias in machine learning. I actually have to look it up. What's the second type of inductive bias? There are actually 6 types. Yeah, choose which ones. Choose which one. Like, no, like inductive bias is just a set of assumptions that you make. I know the set of assumptions. I just have no idea what their name is. But yes. So yeah, but you know, for linear regression, the type of inductive bias is, well, that the input is related to the output. So can actually somebody in the chat or somebody on site? Okay. All right. I'm not used to this. So first of all, the question that was asked in class was, well, aren't there 2 types of inductive bias? And then I said, well, I don't know. And it turns out there are 6 types of inductive biases. And well, you just need to explain the easiest one. I think just explaining one, like saying that you make an explicit assumption that there's a correlation between the input and the output is enough for this question. So can anybody in chat or anybody on site tell me what actually the inductive bias is of can somebody tell me what the inductive bias is of a support vector machine? Do people in chat have any ideas? Because that's a question that might be asked. I believe you're not recording at the moment. I'm recording locally. Yes, you do assume that there's some distinction, but you assume that there's some specific distinction. In SVMs, the way they work is that in some plane, right, you probably learned about kernels in SVMs. In some plane of existence with some slack variables, there should be some linear distinction between the data. Yeah. Yes. This is also what you assume, that in some plane, if you use like the kernel trick, there's a distinction between the data points. Okay. So I'm gonna try to monitor the chat, but it is very difficult somehow. Can I make it stay on the thing always? Well, the linear regression bias is that you assume that your, well, as I already said, there is a correlation between the input features and the output features. So if you want to, in linear regression, predict someone's salary, the features that you input should have an impact on the prediction, should have some correlation with it. Yeah, would that advice for linear regression also be that we assume linearity? Yes, you assume that the output is some combination of linear features, I would say. Okay, so moving on to the next one. As I said, it is actually a very interesting and needlessly complicated. I'm just confused why this is here. Okay, I'm just gonna remove it for now. I wish I could do the same with chat, but oh well. Yeah, the SVM inductive bias, you assume that the data is linearly separable in some way, with either some low number of slack variables or in some higher dimension. Yeah, okay. So now moving on finally to the question number 2. Provide a decision list, and well, a decision list is very actually similar to the decision tree, but the decision list, yeah, well, you basically just make one rule. So what they essentially ask you to do is to summarize the decision tree that you get. That's a nice image of it. Please don't be something weird. Okay. Yeah. The output is linear. The goal is to minimize the sum of square errors. Yes, you assume that there is a relationship and that the relationship is linear. Yeah, by wide margins. Well, close enough. Okay, so let me just see you, man. Okay, so again, decision trees. So what they ask in that question, provide a decision list or the set of rules that corresponds to the decision tree given below. Of course, we need to provide them in the order that they will be applied. For the people online, the screen just disabled itself. Okay, so you need to compress the decision tree, basically, in this question. You need to make some compression, right? Because actually, if you look at the tree closely, we don't need to have all of the features right now. And the way that you could do it is just by looking at the paths, right? You can follow a certain path, and you can see when something becomes a minus and when something becomes a plus. And in this particular picture, you would notice that we have a lot of minuses. We have we have 5 minuses, and we have 5 pluses, and we have 2 minuses. So if we just focus on minuses, we can see that what is happening? Oh my god! Can I disable this? Please don't turn your mics on, guys. Okay. Right. Okay. So the set of ordered lists. Do you guys just not want to hear the answer to this question, or? Okay. So we can see that we only have 2 minuses, and the 2 minuses are actually decided upon one single feature, which is d is smaller than 10. We don't need to know what kind of feature is, but we need to know that, well, when d is smaller than 10, we actually have a minus. and in all other cases, we have a plus. So our ordered set of lists could just be, well, if D is smaller than a 10, we have a minus. If otherwise, we have a plus. Yeah. Any questions about this particular example? Shouldn't it be D is smaller than 10 and C is bigger than 20? So do we actually need from this on this thing to know what C is? Because it is bigger than 20 in all of the cases. Actually, wait. Oh yeah. Okay. Actually, no. Yeah, no. That's actually true. Yeah. Okay. Oops. Yeah. The C should actually be bigger than 20, and the D should be smaller than 10. Yeah. Yeah. Because you make the distinction here. Yeah. Because you only check for D if the C is bigger than 20. Okay. Yeah. Good notice. Yes. I knew this a year ago. Okay, so yeah, we can move on to the next question, validation. So first of all, is it possible to have a binary classifier that on the same test set have the same accuracy but is it possible to have binary classifiers that on the same test set have the same accuracy but different true positive rates and different false positive rates? Explain your answer. Well, from the slides, you might learn that the way that accuracy is calculated is by making a sum of true positives plus true negatives. Yes. What is happening? Okay. Divided by positives plus negatives. Just let me look very quickly. Machine learning accuracy. If it's correct, but I'm most certain that it is correct. Yeah, it was in the slide. It was different. Wait, give me just one moment. What were the slides? So I looked at it yesterday. Okay. Right. Not sure if somebody sent me the. Really, I'm revealing all of the chats right now. I think I've seen the group info, media and docs. There some slides. Yeah, okay. Because I think it's an open book exam, right? So you will be able to keep your slides on, and you really need them. Because yeah, some of those questions actually you need to look at the slides and find out the difference. But I think I already sent this. My computer just refuses to do anything. Okay. So, ML slides, validation. Yeah. I'm just gonna read the chat. Should we, for example, for exercise 2, have 2 rules separately or put it in 1 rule? You can just have 2 rules separately. An ordered set of 1 rules. PTPR, I don't think it is, like, I just forget what it is, accuracy. Fine, next. Yeah, I was actually correct, hey. Yeah, so classifiers validation. The accuracy is true positives plus true negatives divided by P plus N, right? So then the question is, can can two classifiers have the same accuracy but different true positives and what? Wait. True positives and false positives, right? I think it was, yeah. Yeah, true positives and false positives, right? And actually, I saved an image for this exact problem in here. If I can just open it. Right. So we could actually use this kind of image to find out, right? Because what we have is classifiers that have, well, different rates of true positives and different rates of false positives. And what we need from this image is actually the, yeah. What we need from this image is actually the true positives and the true negatives. So we can answer first a simpler question. Can we have two classifiers with the same accuracy that only differ in their true positive rates? Well, not really. If you look at this example, right, let's say that in here we have 5 plus 6. If we have two different classifiers which only have different rates of true positives, then, well, we have a problem because this will get bigger, right? So instead of 5 plus 3, if it was 5 plus 5, it would be like 6 plus 5. So the accuracy would already change. The same can be said with classifiers that only have different rates of only false positives. Because if you look at the image here, we have a fixed number of our examples, right? So by increasing our false positive rate or decreasing it, we basically either take one of the examples or we give it in. But by taking one of the examples, we are taking away from the true negatives. So if only the true negatives would be different between those two classifiers, then it would be impossible to have the same accuracy because you have a predefined, they all train on the same data, so they have a predefined number of positives and negatives. So we would basically be taking away from true negatives. However, if they have both different rates of true positives and false positives, I already forgot what they were asking. True positives and false positives, then we can simply keep this sum at 10, so 5 plus 5 from one classifier, and then the other classifier would, for example, say 6 plus 4. So by changing both the true positives and the true negatives rate, we can, for example, take one extra here, right? Like make classifier a bit better, but then take away from one of the things here. So basically move this one from false negatives to true negatives. So by changing them both, we actually can have different classifiers with the same accuracy, but different true positives and false positives numbers. Does anybody have questions with it? Because you can basically see that, well, what matters for our equation is this part and this part, right? As long as the total number of points in this part and in this part remains the same, we have the same accuracy. So we can vary them a lot. In the true positives, in the green part here, and in the gray part here, we need to have the same number of examples. They need to be, like, the sum of them needs to be equal. And as long as the sum of them is equal, the accuracy will be the same for the two classifiers trained on the same data. Chat. Okay, yeah. Okay, do people online have any questions about this example? Well, apparently not. Let me see. Okay. So the next one is actually, I think, like I'm 99% sure it's weird, because I also remember it from last year. The exhaustive cross-validation method is a method which trains and tests, which trains and the exhaustive cross-validation method is a method which trains and tests classification models on all possible ways to divide the original data into training set and a validation set. Explain whether the exhaustive cross-validation method is satisfied. So cross-validation method being satisfied is not a thing. What they probably mean is stratified, because I also remember it from the last year and it was stratified. I think somebody forgot what it was. So first of all, do people on site online know what stratified means? What is it? Yeah. Yes. So if we have a cross-validation method is stratified if the training set has 60% of positive samples, then the validation set has to have 60% of positive samples. But well, the exhaustive cross-validation trains it on every permutation of the thing, right? It's basically leave one out method, and well, it's not possible for you to just have one example as a validation and then like keep the same thing. So yeah, this is actually this is not stratified. Yes, learn those terms well. You will never use them again, and you will forget them in a year because I had to look it up. But it's fine. Okay, so then compare the computational complexity of exhaustive cross-validation method with that of k-cross-validation. Well, you just can explain that k-cross-validation simply, well, depends on k, right? Like how many, but there's only like a certain number of ways that the data can be split. For example, if you split it half by half, well, there's only two ways, right? You can either take the left part as your train set or the right part of the train set, and the other becomes the validation set. However, with exhaustive cross-validation method, yes, k times n and O times n times n, yes. So as you can see, the O notation, the big O of exhaustive cross-validation grows very quickly with the number of samples that you have. And K stands for in K cross-validation how many in how many parts to split it, and N just stands for the number of examples. Okay, should be fine. Should not be too difficult. Right. So then the nearest neighbor. Draw figure 1, the nearest neighbor regression curve, and the 3 nearest neighbor regression curve for regression problems provided with 4 data points, right? Okay, so for each data point in here, I'm just gonna look at my iPad because I've solved it and I don't want to make mistakes again. Right. So can you repeat the sentence to answer 3b? 3b. Well, yeah. So first of all, the answer to 3b is that the question is wrong. It should not be satisfied like the last word. It should be stratified. And stratified means that when you split it into a test and validation set, you keep the same distribution of your samples. So if you have 60% of positive samples in your train set, then you should also have 60% of positive samples in the validation set. Yeah. Okay. So in this case, the exhaustive cross-validation is not stratified. So it should be stratified, not satisfied. Okay. So this one I want to do together, the nearest neighbor approach. It's easy. Let's at least do the first one together. So we only focus on the closest neighbor, and well, we take usually the average of their points. But if we focus only on the closest neighbor, the average is just simply the point, right? Because the formula is the sum of the values of all points divided by the number of points, number of neighbors. Okay. So if we start, I'm just gonna hope I can draw here, annotate. Oh my God, this is so cool. Okay, so yes. So if we start at 0, right? Okay, I already gave it away. Right, okay, well, whatever. Good enough. Okay, I'm gonna give you a hint, right? So we start at the very first spot. Well, the closest neighbor to us is the one on the position 1, 1. So all of the points which are the closest to it get the position 1, 1. And then at some point, we actually need to switch to the position 2, 2. So when do we do that? Well, the moment that the point 2 becomes closer to us than the point 1, we make an immediate switch. And I'm very sorry for my drawing skills, but you need to do it with a... Oh my god, that's actually good. Okay, so the moment that we reach over the halfway away from 2, so bigger than 1.5, we immediately make a switch, this is a straight line, to 2, because now this is our nearest neighbor. And the same exact thing happens with the other thing. Well, yeah, so, okay. They, okay, all right, I'm gonna put it in place later. So they ask you to draw the nearest neighbor regression curve and the 3 nearest neighbor regression curve. So what we are doing right now is drawing the 1 neighbor regression curve. And then basically falls like that, right? So one of the when we had the exam, when we had the exam review, what a lot of people did is they basically did this or something similar to that, and it's already immediately wrong because because with especially let's imagine this is a straight line, please. Especially with KNN, right? Yeah, they basically just drew a point, but this is how linear regression works. It's not how KNN works, right? Because you don't make use of the points. Okay, so if I can take another section. So now let's draw the k equals 3 nearest neighbor. So the question for the chat and for the people here, where do we start? So let's start at this line, right? Where should we start? Who knows? We need to consider, so from this point, right, from this line, what are the closest 3 neighbors to us? We're only considering the x-axis here. I'm just gonna, yeah, okay. Yeah, so this is 1, this is 2, this is 3, and this is 4 points, right? We have 4 points in total. So if we want to start at the very first point, we need to consider, well, the first points, right? So what are the values of the first 3 points? We can consider the y value to be 1 for the point 1, 2 for the point 2, and 3 for the point 3. And the sum is equal to 6. Very good math. And then we simply divide it by, well, 3, and we get a 2. So we start from here, right? So let's just draw this line up to 1. So where do we go from here? Yes. Okay. So let's keep going to 2. And why do we keep going? Yes. Because right now, like, those 3 are the closest. And you actually might need to use a ruler, but I will just do it with my eye. Which ones are the closest? And so the moment that we get to 3, we have a position of, well, from 3, right? The closest point that we get, 1, 2, 3. Okay, yeah, sure. From 3, it's easy. You should use a roller to make sure, but whatever. So the moment that we get to 3, our closest points are now, well, 1 and 4. They're kind of just as close. So because wait, no, I'm lying. This should be okay. You can use a ruler, but this should be finer. But that's fine. So the moment that we get to 3, our closest points become 2, 3, and 4, right? Because there's a 0 x-axis distance to 3. There's a 1 to 2, and there's 1 to 4. So then we need to use. Shouldn't we switch at? Yeah, we should switch at 2.5, but I already drew the line too far. Okay, well, wherever. Okay, so yeah, we should switch at 2.5. And so at this point, we have 3 values. 2 plus 3, 5, 9. So 9 in total, divided by 3 is 3. So we simply go to 3. and then we just continue on forward. Wasn't too difficult, guys, right? You just consider the values of the closest three algorithms, and you take the average of them. You guys have any questions? It should be like past 2.5. How do we decide if we choose 1 and 4? They have the same distance, right? Yes, well, what calculation are you using here? How do we decide if we choose 1 and 4, they have the same distance, right? Yes, but the moment that the 4 becomes a little bit closer, so before 2.5, like at 2.5 they're equally as close, but before 2.5, 1 is closer, after 2.5, 4 is closer. So we just like make that switch immediately after we reach 2.5, after we reach 2.5, 0, 0, 0, 1, or wherever. What calculation are you using here? Well, so let's say that I start here with kn 1. This is what I would do. So for kn 1, we only focus on one point, right? So it would be like all the sum of all of our neighbors, right? So like point 1 plus point 2 plus wherever, divided by the number of points, right? For kn 1, we only have one point that we have to consider, the closest one, and then we divide it by the number of k, by the number of our neighbors, which is 1. So we just use the value of that one point. For kn 3, if I just do this, kn 3, so for example, when we start here at 0, we consider the first point, the y value of the first point, which is 1, plus the value of the second point, 2, plus the value of the third point is a 3, divided by, well, 3, divided by k. Actually, oh yeah, I'm just now realizing this should be k, not. Whoops. Please. This should be k, right? Yeah. And k is here equals to 1, and k here equals to 3. So just the average of all the points. Are we taking neighbors of a point x0 at the beginning? Yes, yes we are. Because, while our points right here fall nicely into 1, 2, 3, and 4, we might need to know what we do with a point of 0.8. So let's say that we have, a 0.8 here. Here. We cannot just say, well, we don't know, we give up, right? So if we cannot say we don't know, we give up for this point, then we can also not say, hey, we give up for this point as well, right? Because it's just a simple line. Like it is possible that you would have some points at like -1, and this would be the closest neighbor. Yeah. Okay. So this one would also be here. So if we don't have any training points there, then this line would also just continue going there into that direction. Okay, clear? I'm just gonna clear everything because otherwise it will stay on my screen, right? I think so. Yeah, it will. Clear. Okay. You can watch it in the recording. Pause it if you want. Yes, so next question is, so this is a very simple probability question. Suppose there's a fraction of undergraduate students who smoke. Suppose the fraction of the undergraduate students who smoke is 15%, and the fraction of the graduate students who smoke is 30%. If 1/5 of the college students, or 20%, are graduate students, and 80% the rest are undergraduates, what's the probability that a student who smokes is a graduate student? So who can answer this question for me? Yeah, Good question. Uh, this is very basic probability, I guess. And I think you had something about Bayesian learning, very briefly, very complex, not enough time spent on it. Yeah, I think this is an attempt to still push it into the exam despite it not being explained well. Yeah, exactly. Okay, right. So, yeah, I'm gonna just ask you guys to do it. So, can somebody in the chat tell me what I have to do? How do I calculate the probability that a student that I randomly took from the whole university is a graduate student who smokes? Mm-hmm. Yeah. So first you take the probability of somebody said in class. You first take the probability that, well, that they're a graduate student or the undergraduate student, which is 20 and 80 respectively. And then you take the probability, well, that the graduate student smokes, right? So what we get is, okay, annotate. What we get is simply, well, let's first check if a student that we took, this person, if he's a graduate student, and the percentage of him being a graduate student is 20%. 20%. That says like a graduation hat. Hmm? Mm-hmm. Yeah. So you just need to use the Bayes theorem. Oh boy, the Bayes theorem. Okay. I actually need to look it up because I have no idea. This guy is gonna keep following us. For now, how was it again? Okay, the positive user, positive. Okay, cool. Yeah. Oh, that's revealing too much information. Okay, so yeah, as Lars mentioned here, I cannot find chat. Okay, as Lars mentioned here, yeah, the probability that he smokes despite being a graduate student times the probability that he's a graduate student plus the probability that he smokes despite being like the graduate student, and then, well, yeah, it's just a simple Bayes rule, but because I don't want to put in, like, I can handle it later if people have questions, but like it's just a simple implementation of the Bayes rule. I think you had it last period for the statistics. Yeah. Okay. So wait. Mm, wait. Yeah. Yeah. You need first the Bayes rule and then yeah, the one on the bottom. You right. The law of the probability. It's gonna be like yeah. Yeah. Okay. Big grad smoke. Yep. But it should be fine. Like I think you solved the exact same thing for statistics, probability statistics. Oh, really? Okay. Yeah, I've never had reasoning techniques. I did do the pre-master last year, but like I also a bit struggled with this exam because I was kind of sure that I knew a lot of machine learning, which I did, but I didn't know like this part of machine learning. You know, like oh yeah, how does yeah, for example, like I basically skipped over this like thing. I was like, oh yeah, it's easy, and then I just never looked at it. Okay, that's fine. So now let's go to my favorite one. Oh no, wait, no, my favorite one is actually the next one. Okay, so this is my not favorite one. This is actually my honestly favorite one. The next one is my sarcastically favorite one. So we need to solve a multi-class problem when the training data samples include 25 different features, which should allow us the identification of 7 different species of flowers. We also know that the problem will require the implementation of a complex nonlinear function. To solve the problem, we decided to implement an artificial neural network. And well, they ask us to describe the network. You would propose to justify the selection of the following parameters: number of neurons in the input layer, mean number of hidden nodes, and number of neurons in the output layer. Okay. So, shouldn't be too difficult. What's the number of neurons in the input layer? The text, okay, I can make it bigger, no problem. Just gonna, I can't make it smaller. Nope. Okay. Okay, this is sad. Okay, I'm just gonna remove chat for now. Yeah. So we need to, well, number of neurons in the input layer, mean number of hidden layer, and number of neurons in the output layer. Yeah. So as somebody in class said, you will have, because you have 25 different features, well, it makes sense that we input 25 different different neurons, right? But what I would also do is honestly add 26 different neurons in the input layer. Do you guys have any guesses what the last one stands for? So we have 25 features, and we have something more that you might have learned. Yes. We have the bias node. Yes. So we're going to have just 25 plus 1 is usually how I would write it. So let me just annotate. So 25 plus 1 is usually what you would have. So then the mean number of hidden layers. Anybody have any guesses? Hidden layers. It's not hidden nodes, it's hidden layers. Because hidden nodes can be wherever, dependent on your problems. But well, yeah, so because we don't actually need two layers, right? If it's, do we need the layers? Oh. We also know that the problem will require the implementation of a complex nonlinear function. No, we would need to, we would be able to just simply solve it with one layer, because in that one hidden layer we would be able to use as many neurons as we can, like as we want, like a few thousand. So we need at least one, because I think it might have been mentioned, but there's a theory that if there exists a mapping between input and output, doesn't matter which one, it can be solved with just a single hidden layer. However, you know, what they don't tell you about. Yeah, if you don't need a hidden, if you have a linear layer, you would be able to basically have, because the output layer also has its weights. So if you just have a linear layer, then I would not even like do a hidden one, because it's more simple. But yeah, so yeah, as it says, I'm not sure if you guys got in the lecture, but yeah, if there is a mapping between the input and the output, then the problem can be solved with just a simple hidden layer, with one hidden layer with an undefined number of neurons. Of course, well, that undefined number of neurons could be almost infinite, depending on the problem. And well, what it also doesn't tell you is how well it generalizes, right? Because you could say that other networks which have more difficult architectures generalize better on unseen problems. But that's something that I think is a bit out of the scope of this course. But yeah, if you have some mapping between input and output, one hidden layer is always enough, at least. Okay, so one. Number of neurons in the output layer, well, that's easy, right? We just have 7 classes that we want to output. But how would we do that, actually? I'm not sure if you had that, but like, what would be the example of our output? Yeah, if we activate it with a sigmoid function, yeah. So let's say, right, what we're gonna have. I'm gonna just clear this one to make room. So I'm gonna handle this part of the question here under. I'm gonna remove it after. Okay. So I'm actually not sure if you guys had it, but let's make it a bit fun. So let's say that we have some output, and some output is usually a vector, right? It's represented in if I can just draw circles, would be great. I'm going to draw ones because it's easier. 1, 1, 0, 1, so 4, 5, 6, 7. Oh, whatever. Okay, right? We are familiar with this output before. I'm not sure if you guys had it, but it's actually a very interesting trick. So we have a problem actually, because how many classes can we represent here? Just if we only have a single one, and yeah, basically, like how many classes can something like this represent? Because usually the way that you do it with a sigmoid is you take either the highest class, or like, yeah, with the sigmoid you basically say that it very quickly becomes a 1. But we have a problem here, because this can actually represent more than we need, right? Because we could have a 1, right? Like a 1 here, like this type of flower, 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 this type of flower. However, we can also have something more, and I'm actually like kind of fishing right now for somebody to tell me, because if you didn't have it yet, then I'm also not going to speak about it. I'm going to speak about it very briefly. So Lars, do you have an idea? Always turn to Lars. Softmax. Yeah. No, yeah, so what I was talking about here is that actually by defining 7 output features, we actually have 8 possible things that could happen, right? Because our network could also tell us that it's not sure that it's any of them. Because usually what you do is you basically, say that if the probability is bigger than 5, then it's that class, right? But the problem is that, well, the network can also tell us that nothing is here correct. So one of the examples that we could get here is 0, 0, 0, 0, 0, 0. So basically we let the network kind of waste some space on trying to represent this feature that we are not going to be able to use. So what people do, and I'm like seeing the faces here in class, you didn't have it, is they simply make the output of the network k minus 1, where k is the number of classes. It's actually 5. Okay. Yeah. So here you have 7 inputs, right? And here you only have 6. So we can have a 1 for each of the 6 flower classes, and if we have the 7th flower class, we actually have a 0. But dimension reduction. What's that called? It's not particular dimension, but it is kind of dimension reduction, because you make it simpler for the network. Because by allowing it 7 outputs, you actually tell it that, well, that you leave the possibility of having all zeros. Because you also have weights for every single one of the output layers. So you're kind of taking the weights out for the last output layer. So kind of, but it's called differently. It's called differently. It is, yeah, I forgot what's called. But if you don't know it, guys, you don't need to know it for the thing. It's just like a cool little trick. Clear. All drawings. Okay. Yeah. Should be fine. Okay, draw an ANN architecture. That means the features which is described in the previous section in drawing make use of a locally connected layer, clearly point in the drawing. Yeah, so locally connected layer, the way it's called here is just, well, what they mean is, I don't think you had the fully connected layer. So wait, or did you? Give me a second, I'm just gonna check your presentations because I really don't want to confuse you guys. I already confused you a little bit with like talking about that outputs, but it's fine. Do you actually have? Yeah. Okay. All right. So you did have like the actual locally connected layer. Okay. Yeah. So what's the difference between the locally connected layer and the fully connected layer? Guys, the difference between the locally connected layer and the fully connected layer? You're googling it. Okay. So the fully connected layer is funnily enough, fully connected. So if we have a simple network where we have a node, yeah, so 2 input nodes, 3 hidden nodes, and 1 output node, which could be a binary classifier basically, because it's either 1 or 0. Like it's basically the same idea as what I explained, right? Like by removing, but we have basically 2 classes, binary classifier, but we only need 1 output because if it's a 0, it's 1 class. If it's a 1, it's another class. Okay, so the fully connected layer, oh boy, here it goes, I'm gonna actually do it in another color, would go something like this. This is a fully connected network, right? What does it mean is that every node in one layer, for example, in the input layer, is connected to every other node in the next layer, right? And the same holds true for the hidden layer and the output layer. So the locally connected one, simply what that means is that not all nodes are connected to all other nodes. So what you could do is simply say like, this is a locally connected network. Why? Because this one is not connected to this one. So it's kind of locally connected. It's not fully connected. And then you would like basically say like, look. Yeah. LCN, which stands for locally connected layer. I'm having a bit too much fun with this. Okay, so that means the features you described in the previous section in the drawing. Yeah, you can. I trust you guys that you can draw with 25 nodes. But yeah, the way that I did it on the exam is I simply said like 3, so like 22 more basically, because I also want to save some paper for maybe other people. Okay. So yeah, all right. So yeah, the question: are there at least requirements for an area to be locally on the edge, not between all neurons, is enough? Okay, can you draw it? No, I can't. I literally will not have enough space, and it will be such a huge waste of time. But yes, like what I already drew basically says, yeah. So a fully connected layer simply means that it is connected to all of the neurons are connected to every other neuron in the next layer. A locally connected means that it's not true. So like one less layer is technically a locally connected layer. How many output neurons are there? Because you said 8, then... So the output neurons, I said first 7, then 6. But because I thought you might have had that part where like you remove the... you basically, instead of outputting k classes, you output k minus 1 classes. But... having said that, yeah, no, this is actually not the receipt exam. This is the first exam for machine learning. How many neurons you should draw in a hidden layer? Well, that's up to you, because you actually did not define how many neurons your connected network had. So you can just draw like 2 neurons, right? And then you connect like half of them to 1 neuron, half of the inputs to 1 neuron, half of the inputs to the 1 neuron, and then to the other neuron. More than 2, otherwise local gets difficult. I just draw 1. You just draw 1. I mean, you just draw 1, Lars. Don't draw. Yeah, I did the pre-master last year, and this exam was the first exam. So it wasn't the January exam. You can also see, like, because the January exam would be like 2020. I'm most certain that I've seen this somewhere. So it had to be like that. Oh well, whatever. Um, maybe it was the receipt. But okay, so yeah, I just draw one. Lars, don't draw one because you can't locally connect. Why the okay? Yeah, right. So please forget about k-1. I confused you accidentally because I thought you had it. I thought I had it during the course. No, not one plus bias then. Like there's no bias in the output layer. Oh well, whatever. How many hidden layers did we say? The hidden layers is just one. So 7 neurons, at least one hidden layer. Yes, at least one hidden layer, and no, yeah. So 7 neurons for the output. I confused you accidentally. It's more complicated concept. I'm sorry. Lars, you are now uninvited from machine learning club sessions. Okay, so with 100 neurons each. Yeah, okay, sure. All right, so let's go to my less favorite. No, I'm joking, Lars. You're always invited. And so are all of you. Please come. We're going to have state of the art on computer vision. It's going to be very fun. I'm going to explain every single computer vision technique that they've used in that paper so that it's also understandable for even first years. Please come. Okay, so, right, okay, cool. So we have, oh yeah, we might have forgotten the bias node here because we had the bias node in our network. Whatever, it's fine. Yeah. No, like I'm 100% sure that this was not the receipt. Like I'm 100% sure. Yeah, no, because of this question, because I know from a fact that this question was not in the receipt. But yeah, no, okay, but it's fine. So right, the activation function used for all neurons. Okay, yeah. So here we just need to compute the the properties over every single. Yes, this exam was supposed to be 3 hours. Okay. Yes, but like I was done maybe in like 2 hours with it, or even less. But like yeah, some people maybe needed some more time. Yeah. No, like the most fun thing starts when you spend 2 hours on the exam and then you have 1 more hour and you don't want to go back. So you start like checking all of your answers and you're like, did I do it right? And then you did, but then you change it and then it's not right anymore. That's fine. So yeah, okay. So the activation function is used here. So we have the activation function here for simplicity. Okay, yeah, all right. I know again how to work it. And these are our queues. Aren't they supposed to be thetas? Yes, this is 1, 1, 1, 2, and 2, 0, and 2, 1. Okay. So what I'm going to do is I'm going to come back to this question because I really don't want to do this. So I'm going to just explain like the simpler questions right now, the question 8, and I'm going to do, yes, that is very annoying to do because you just need to like from the slides implement, like use the algorithm and then put every number into every direction. But yeah, okay, so let's start with question 8 for now. Because it's actually a lot more important. Explain why the plot cannot have been generated with gradient descent. Provide proper proof using math. Explain your test and draw into the plot how gradient descent would actually behave if you properly implement it, execute it. Yeah. So the way that this question was asked during the exam is like some student handed this in as his gradient descent thing, and they're suspecting that he just like put the crosses here. Which, funnily enough, in Python, it would be easier to just implement the gradient descent than to put crosses there. Yeah. So right. So and I also saw in the group people being confused because this is the exact same image that they used last year. That they used in the presentation, and they used it last year as well. Like this exact same problem, which people were confused about. But yes, as somebody also mentioned, I think it was you, Lars. The crosses have to be closer together the closer you are to a minimum. So this is the minimum of the function. This is the point that we want to find. And the gradient descent basically goes like this. And well, the last thing that you want to do when you're optimizing a function is to overshoot, right? So the gradient descent looks at the first derivative, and well, the first derivative gets smaller and smaller and smaller. and then at some point he just like, well, stops stepping it, right? So he would take very big steps here and very small steps down the middle. And then you could prove it using mathematics, because there's an algorithm for gradient descent, and you would just say, well, yeah, the first derivative gets smaller, so it cannot be as big. Do you have any questions about particularly question 8? Why the plot was generated? I hope this kind of question doesn't pop up, since it's basically a big L for anyone doing the exam online. You mean the gradient descent question? Is a problem for people doing exam online? Having to copy the plot. You don't have to copy the plot, you just have to explain what's wrong with it. So like you can just like type in here, you know, like, hey, this should be smaller, and then you give the equation of the gradient descent, and then you say, oh, well, the closer we get, the smaller the first derivative becomes. It says mark what it would look like if it's not properly, right? Does it? Oh boy. Okay, yeah. I actually missed this one. I think my brain just left it out, hoping that it wouldn't come up. Yes, the session is recorded locally for me, because I can't seem to record it via this thing, but it's fine. Okay, yeah, so this session will be online, I hope. It's recorded. It is recorded, hey. Okay, cool, yeah. Yeah, okay, perfect. And the chat is also recorded, so everything you say will be used against you. So, explain with your own words the purpose and use of Slack variables in SVMs. Under which circumstances are Slack variables useful? How are Slack variables applied? For your explanation, make the plot with example data. Oh boy. Okay, why is this so much drawing? Actually, I think I start remembering why this was a 3-hour exam. In the plot and in your explanation, compare what happens if Slack variables are used with what happens if Slack variables are not used. You will be able to find the recording on the official Machine Learning Club YouTube channel. For a while, at least. I might remove it after a while because it's more about the papers and whatever. Okay, yeah, so back to the exam. So the questions, the Slack variables. So does anybody on site or online want to tell me what Slack variables are? I kind of gave it away already at the start of this. No, did I? I don't know. Okay, Slack variables for SVMs. Okay, so here's the thing, right? I'm gonna draw it here because it's easier and I have a lot of spots. When data is not linearly separable, yeah. So, but Slack variables allow you to have better model but on mistakes, I think. Yes. So that's true, but well, yes, true, but it doesn't capture quite what Slack variables are. So let's have fun with Slack variables because they're always fun. So let's say that we have positive examples here, and we have negative examples here. Well, that's perfect, right? We just draw a simple line through it, and then we are done, right? Oh, that's nice. Fortunately, the world is not as nice. What happens if by some mistake we got like a, oh wait, I'm gonna make it easier, minus here, and we got like a plus here. Ah, that's a problem, right? What do we do? Well, so Slack variables is a horrible name for it, but having said that, Slack variables kind of does capture the way that this problem was solved, as in the person who came up with them slacked a bit. He got tasked with solving this issue, and this is what he came up with, right? So we could draw a line, right? But then the data would not be linearly separable. But guys, let's consider for a moment that we would introduce a Slack variable, right? Which would only work for this thing, right? So the Slack variable only works on those outliers. So, you know, I know that the data is not separable, but hear me out on this. What if the data that makes it not linearly separable, we just moved to the other direction, and then it's linearly separable, right? Like, it's perfect. I don't say, like, what if we just like didn't consider it and just moved it to the other direction, right? Then it's, well, you know, then we just ignore that this has ever happened, and then we have like a new one here, and it's perfect. It's linearly separable. Yeah. Yes, it is a bit odd. It is basically like I think like the way that it was named is like, yeah, I could think of like some mathematical way of actually solving it, like a kernel trick. But, but hear me out on this. What if we just ignored the points that do not fit into our data? Yeah. So slack variables are actually point specific. So you have a point xi which and has like some bias, some calculation, whatever, doesn't matter. And then it basically has a slack variable, and you can see the xi and the slack variable I. So it's only the slack variable for this point. That's the same thing, right? So basically indeed, as you said, it allows for mistakes by saying, well, what if those mistakes never happened? Like, hear me out, guys. It's smart. I'm a smart researcher who. Yeah, so you basically try to find slack variables that make the data separable. And you want to usually minimize the amount of data that you can move. Because you can also just add a slack variable potentially to every point and just like, easily. Yes. Yes. Okay, so hopefully that was clear enough. Explanation, what happens if a slack variable are you in the bottom? Yeah, so you need to draw it, but like I just drew it, so you can do something like that. Are slack variables specific to SVM? As far as I know, yes, because SVMs specifically expect a linear separation of the data. So if they are not linearly separable, you just make it linearly separable. You basically force your way in. There are, of course, other solutions for this particular problem, but yeah, this is how it used to be. And they're actually still used for some if you have a low dimensional data, which is usually linearly separable, then you might actually want to use it, right? So like what we might have is, you could use a kernel for that, but we could have points here, which are pluses, right? And here we have the minuses, right? And the minuses are very sparse, right? So let's say that this is what we expect to get, right? Let's say that this circle is perfect and it fits as tightly as possible around this thing, right? This we could achieve with a kernel, and we could say, well, this is what we expect to get. Like, this is good data. Like so somebody has checked, maybe an expert. So let's say about some brain MRI scans that are looking for tumors. So you have a data set of images, and some researchers, some medical professionals said, okay, so these brains do not contain a tumor, and you have thousands, like tens of thousands of those pictures, right? And then any deviations from that 10,000 normal brains you want to find, right? Because even like the smallest of tumors might prevent it, right? So basically, SVMs are used when the detection of anomalies is very important, right? Like you want to say, oh, this is a bad thing. Like if it's even if even there's a slight brain abnormality, and it's like here to the edge, you don't care. You just immediately say, no, this is a problem. Like we might need to explain it, right? It also helps medical professionals because they can just like let the machine tell them whether the thing might be explored further. Why no medical professional actually does that is a whole other discussion that we will not get into right now. But this is some place where they could be used. Okay. Right. Okay. So hopefully I have answered everybody's question. Please don't go away. Imagine you're working in a company that solves data analytics and prediction problems with machine learning techniques. Yeah, the company you asked us to identify which machine learning technique is suitable for the problems proposed by your customer. You can hear it in my voice. I don't want to read it. Formulate 5 independent questions that you can ask your customer to identify suitable machine learning techniques for your customer problem. For each question, shortly name techniques that would be suitable depending on your customer. Well, I could do that because I could just like take the state of the art that I've read. having said that, guys, I want you to do that. Let's spend some more time on it. So people in the class, people on online, what would be a good question to ask for a client? So he comes to you maybe and he wants he wants to tell you basically, he wants to, for you to, from his data, find out whether, from some blood pressure, from other tests, he wants to find out whether the person has brain cancer, right? From some pictures, wherever. What would the first thing that you do ask? Does your ice cream sales vary with the murder rate of the city? That's something for you to find out, right? So okay, let's say that you have some blood pressure, some maybe images, wherever that you define as some numbers. So why would and some people had cancer diagnosed, some people did not have cancer diagnosed. That's basically what he tells you. That would not fit well into the problem, because this specific problem is labeled, right? You're not looking for some deviations from the norm. You're looking for a specific diagnosis. So they should be labeled, right, by somebody. No, like so I gave you a problem, and you need, so basically what you need to do for this question is think of a problem, and then think of how to solve it and which questions to ask for the client. So yeah, so identify which machine learning techniques is suitable for the problems proposed by your customer, right? I'm your customer. And I tell you, I have some medical data, and I want you to find out whether the people have cancer. What is your question, the first one that you ask me? Well, no, but you need to think of a customer who might have a problem that you can solve. Um, sorry, what do you mean? Yeah, that okay, guys, but to also they think about some machine learning technique that you might use. So, for example, just from that, right? We have medical data, and we want to know whether the person has cancer. What is the first machine learning technique that you would use, right? Mm-hmm. Well, so the question is like, if you have features, wouldn't the first thing that you want to know whether you have supervised or unsupervised technique? But like, but if you want to label if a person has cancer, then it's already supervised. Yeah. Yeah, you can assume, you can create any problem that you want. The point is not to create general problems. The point is to create a problem and then suggest a machine learning technique which could solve it. For example, like when it comes to to classifying whether asking about the desired output probability. So this is one of the ask about your ice cream sales. Okay, so Lars says ask about the structure of data. Yes, but you need more specific questions. Is data labeled, as in the features target? Well, yes, but usually, like if you want to find out whether people have cancer, you assume that they're labeled. So I wouldn't say this question would rate highly for this question. But the next one, asking about your desired output, probabilities or Boolean. So what are you trying to find, right? Are you trying to find the probability that that the person has cancer? So this person has 90% probability. This person has, or are you trying to find out whether whether the person has cancer or not? Like, do you want to give some probability? Maybe like this person has 4% chance of having cancer against the other person. Just basically in kind of anomaly detection way, you would in the kind of anomaly detection way, you would basically tell it like if this data in any way deviates from the one that we've seen, then we treat it as an anomaly, right? So for example, if the customer would say that, well, I actually want a probability that this person has cancer, because I already suspect that he might have cancer, and I have data, and I want a probability, then you might use something like a binary classifier with a sigmoid function, which with some probability, basically a regression. Yeah, you basically would regress that, and you would regress over the probability, and say, okay, yeah, so I suspect this person might have cancer, and based on the data that I've collected on the experiments, it has a 90% probability, right? If it's only a Boolean, then you might want to do something like an SVM, right? So does this data fit into the general distribution of people who do not have cancer? Something like that. Okay. So who has a different customer? What kind of machine learning problem can be solved with what kind of problem can be solved with machine learning? So we're asking the network to basically find some hidden patterns in the data. So what kind of issue could be solved? So we have classifiers, we have regressions, we have whatever else. The class of the database is specified or not? Okay, yeah. So, well, the class of the database is specified or not. Yeah, so, yeah, but you also need to have a customer, or you're talking about the same customer, about the cancer, the brain cancer guy. Yeah, this is actually a more or less difficult question, basically, because you need to propose one customer, but then like you need to ask him questions. Like this is where most of the time went. Not necessarily. Yeah, but okay. So what would be the easy customer? What would he have? Yeah, it's difficult because you need to also well, yeah, you need to find out. Yeah, I don't think you have enough experience yet to actually answer the question well enough, because you need to answer. You need to know like different problems and different ways that you can interact with the customer. So yeah, but I still want to do it. Yeah. So okay. So we can just go like for the brain cancer guy, the customer. We can go in different directions here. We can go in different directions here. What do you mean in different directions, Boris? We're waiting for you, Boris. Now, yeah, we can think of many customers. Yes, you can think of many customers. And then you need to ask the question. But the way that I approach it is basically like, okay, so in which cases, would I use supervised? I don't know. Have you had reinforcement learning yet? Okay, yeah. So in which cases would I use like reinforcement learning? In which case would I use labeling and whatever? So yes. Yeah, okay. I'm actually also having trouble with it. What's a good customer and what's a good question to ask? Let's see what topics did you guys have. This is not I want. Based learning, linear regression, SVM, SVR, clustering, RL. So a person, well, yeah. Okay, so a very general customer, let's just say, he wants to improve his business, right? He wants to improve his sales. What do you ask? A bit of an easier problem, I think. The first thing. Well, the first thing that I might ask is, well, do you know something about your customers, right, already? And do you want to relate it to other new customers? So for example, whether those customers are maybe active or inactive, right? That would already be a labeling, a supervised learning problem, a classification problem. Or do you just want to know something about the customers, like how they're related to each other? In the second case, you would be using some clustering approaches because you want to by maybe using some data about the clients, you might want to say, okay, so this data is this or that, right? So based on his buyers, like this customer is probably a woman, so we might want to give it ads that are targeted for women. This person might be a child, this person might be a man, and something like that, right? That would be already a first. How much data are we given? Okay, how much data are we given? And wait, I'm gonna just go to the other. Okay, you can ask about the general direction of the problem. Do you want this to interact with? Do you want to find similarities in data? Do you want to give answers about the future data? Yeah, exactly. And then for each of those questions, you would basically find the machine learning technique you would use. How much data we are given? Okay, why is that important? That's a good question, but why is that important? Definitely. So then you might, yeah. So if you have this kind of problem where you have a lot of features and very little data, what you usually could do, I'm not sure if you guys learned it, but you would be able to try to analyze, okay, some analyzations of what kind of weight do the features have on each other, right? Yeah, it also defines how complex your model can be. So if you have 1,000 pictures, well, you probably should use some 1,000 pictures of cats and dogs. You might want to use some not deep learning approach, right? You might want to separate them based on some, well, maybe created features or whatever. If you have millions of pictures of cats and dogs, well, then you might as well just use artificial intelligence, right? By inputting as much data as possible and then learning better presentations. Okay, right. So now we say, okay, so the customer has a lot of clients, and he wants to learn something about those clients, right? So what's next? He doesn't know what he wants to learn, but he wants to learn something. And because we have a lot of data, we probably we have little data. We're gonna use non-deep learning approaches. It's always in these questions easier to work with not a lot of data. And because he just wants to learn something about the clients, we're gonna use some clustering. Yes, indeed. Another good question is, Arthur, if the data contains continuous or discrete variables, right? So what kind of variables do we have? Do we have some labels? Do we have some real value targets? Like maybe like a salary of a person that you somehow got to know. Maybe you have some labels whether he has bought this specific product and something like that, right? And what if he did have a combination of continuous and discrete variables? What are we going to do? So the customer has the salary of a person. Your customer has the salary of a person somehow, and he has a label with the gender of that person. So how would you input it into the network? You could make it discrete to put it into different different classes of like maybe lower class, middle class, and upper class. But for example, if you have a label with the gender of a person, what are you going to do? How would you represent that data? Because you can't just put like man, woman, or I'm trying to be very inclusive here, to non-binary. You can't just put one of those three. We can map them to real numbers. Yes. Is the problem linear or nonlinear? Does your so yeah? First of all, we can map them to real numbers. Yes, you can map them to real numbers between 0 and 1. So for example, if you have 3 classes, man, woman, and non-binary, would have like 0.3, 0. No, actually no. Yeah, no, we would actually have no. Yeah, we would basically be able to discretize them by having a simple vector of 3 numbers, and it would be like 1 0 0 for a man, 0 1 0 for a woman, and 0 0 0 1 0 0 1 for the other. So is the problem linear or nonlinear? Is that a question that your customer might answer? You know, like he's like, what? Like, what is linear? Like, what is that? Because like, you know, if the customer can tell you whether his problem is linear or non-linear, that's, you know, he will not need you. Like that's, you know, your job is done. That's fine. But yes, like you need to also understand here. You need to infer some of the machine learning techniques from his general questions. But I think it's enough for now. Let's not spend too much time. How much? How much do you pay? If it pays too little, we will only use linear regression. All right, guys. Okay, so, and here's like a classification problem, and you use linear regression because, you know, because it makes sense, and then it's perfect. Okay, so given the following data set, show with drawings and explain with your own words the different steps of K-means algorithm. When k is equal to 3, show and explain individual steps of the algorithm, not just full iterations. Okay, we don't have any drawings, funnily enough. But having said that, we actually do have a solution. Okay. I'm just checking very quickly my messages to see if I'm not going to reveal anything weird. Okay, so I need to go to the D key. Thank you guys for bringing it to the top of my chat. Oh wait, no, it was actually sent to me privately. Yes, Yumao, thank you. Okay. It's complicated, guys. This is why, like, I don't like this. I think it was maybe him that gave me the numbers. I'm sorry for revealing our private chats, but okay, I think it was. Yeah. Okay, perfect. I found you, the unnamed person. Okay. Yeah, they put into the 6th assignment now. Yeah, true. So hopefully you didn't do your assignment, guys, and then we can handle this as a kind of thing. Because there's actually another assignment, I believe. Yes, it was the Andre. It is the same one from the assignment. Yeah. Yeah. Thank you, guys. Please tell me, is this one? Okay. Interesting. Yeah, but we can find out the answers, like, not too difficult. Yeah, the K-means algorithm. Yeah, they probably won't recycle their questions, yes, Lars. So, funny thing is, one of the professors for one of our courses in master had to put out the statement that the questions found in the mock exam are not representative of the questions in the real exam, because some people complained. So I'm just putting it out here as well. Yes, so you will not be asked the exact same questions, guys. Yes, it's yeah, if only. Okay, so yeah, let's do the K-means. I don't know, guys. Has the deadline passed already for this? Like, have you done it already? Oh, okay, cool. So I'm just solving your assignments. Do you get graded for it? I cannot solve it then for you, because it would be okay. This is bad, because it would be plagiarism if I. Okay, I actually cannot solve this for you. I'm sorry, guys. Okay, that's unfortunate. But I can create a totally new assignment and solve that one. White. I'm just gonna get a full white background to draw on. This is fine, guys. This is how people do it. Please give me the white background only. I don't care. Oh my god. Okay, we're gonna have a. Okay. What? Okay. Okay, perfect. So then I just have to F11 this. Okay, hey, we found our whiteboard. I don't even need to do anything with real life. Okay, so cool. Oh, open paint here, guys. Thank you. Oh boy. Okay, so we have a totally original assignment. I do not know if I get in trouble for this. It's your fault if I do. Okay, so we have. It's actually a bad idea. We have 3 points here. 3 point here, point here, point here, point here. Yeah. So funny thing is the things there actually like work out. We will have like the k-means 2, so it might be that we take like a long amount of steps because I also have to choose now where to put the centroids, which is easier said than done. Having said that, I will put the centroids here, and I will put a centroid. Yeah, I will put a centroid here. I'm gonna have blue against red. Okay. Please don't tell me we already solved it. Right. Very quickly. Just gonna very quickly find what k-means was. Oh yeah, okay, cool. Yes, yeah, initialize centroid, pick seed, reassign clusters, compute centroids, and reassign clusters. Okay, yeah, that's easy, right? So I cannot copy this, can I? That's a problem. Oh, it's gonna be a lot of drawing. If the so the points here don't move, like the black ones. So if they do move on the following slides, just ignore it. Okay, so I have one here. Okay, so let's first of all compute the clusters. And the way that we're gonna do it is just by simply saying that we have a red one here, a red one here, a red one here, and I solved it probably in like one. Oh no, actually I didn't solve it. Haha. So I did do it well. Okay, we have a blue one here. Just gonna very quickly do this. Yeah. So we have a blue one here. So this is the centroid, right? A blue one here, blue one here, blue one here, and blue one here. Yes. Okay. So, and these are the actual centroids. Please, guys, stop messaging me. Yeah. Okay. So we have computed the centroids, and now we actually have to find the average position, right? So what we simply did is we randomly, or in this case, well, to make it more interesting, assign the centroids the random centers of the clusters. So first of all, I want to ask a question that might as well very well come up during the exam. So because we assign random centroids, we start with random centroids. Is the output actually stable? So in k-means algorithm, right? Even though we start from different centroids, but we try to fit the clusters as well as possible, will the clusters be the exactly same every time you run it? No. Why not? Because actually the path through the data points is not defined, right? So we have we have centroids here. Oh boy. Okay, centroids here. Yeah, this is centroids and this is world. Okay, so right, and then we recompute basically the average position of those clusters, right? So our new centroid for the red one is here, because it's kind of the average position. I'm gonna make it bigger to make it more clear. And our average centroid for this class is, well, somewhere here, right? Okay. So on the next iteration, we will on next iteration we will move them, right? So we now have computed the new centroids, and we see that our clusters do not stay the same, right? Because now this point actually becomes red because it is closer to red now than it is to blue. So this all points stay blue, but this point now becomes red. If any points change when you reassign the centroids, and the centroids themselves are not points, they're just random. They're not data points, they're just random points that you chose. So you should continue until there is no reassignment of any points. That can take a while. But let's do it for now. So we have centroid here, we have centroid here. And so we redraw them again, basically. Is what we have to do. So we draw it here, we draw it here, we draw it here, here. So this all four, they stay blue because they're the closest to the blue centroid that we calculated, the average one. Yeah, but now this blue point is the closest to this red centroid. So we get. Wouldn't this really be bad with lots of noise? The thing is, right, with clustering, you don't really know how much noise you have. Because, why? Well, because you don't actually know what you learn about the data. So you don't know like how much noise or how much good examples you have. Clustering also, it's called a k-means clustering, and in this case, we chose k to be equal to 2, which means that we have 2 clusters. But we could also choose to have 3 clusters, or we could have 5 clusters. And then we would have also more points moving. So it would be difficult with, if you had like a lot of data that was very close to each other, not very far apart, then you would actually have a problem with, the number of points in a cluster, and which cluster belongs to what point would be completely dependent on where you started your centroids. So like imagine if this whole cube was, if this whole square was populated by black points, then, well, it would be very difficult to actually like separate them. So you do need some sparse assumption, some kind of a sparse assumption. But I'm going to continue with it. So we have this here, we have this here, we have this here, we have this here, and then we have reassigned the points, and we calculate the average positions of the centroids, which is here and here. And so we can see that the blue points are the closest to the blue point, and the red points are the closest to the red point. So in the exam, you just had to write down all of the steps that you did and what you're doing and why this makes sense. And the moment that we don't need to reassign the points anymore, we are done. Hopefully they stayed kind of consistent. Actually, completely not, but it's fine. What happened there? Okay, yeah, so yeah. And now all of the points are consistent. Do you guys have any questions on this particular algorithm? Can you say a quick word on time complexity, please? Well, time complexity is very difficult to define because it is also depend on where you start, right? It could be possible to start the centroid in the perfect position, right? So that you would have only one iteration. You have one iteration, and well, and you basically are already there, right? Because you just randomly chose points. It is unlikely, but it could be possible that are already connecting all the points that don't need to be changed. However, like it would take quite a bit of time, especially on large data sets with lots of features, lots of dimensions, to calculate them all and to compute those centroids. Because like computing the centroids themselves is not very cheap computationally. Because you need to take all of the points, and now imagine you have 1,000 red points, and you need to take the center of all of them. Well, it's difficult because you might need to like have some Euclidean distance between them. So it's dependent on your data set and how many points you have. But this should be fine, unless you guys have any questions. Close. Okay, so right. Yeah. Okay, so let me just annotate. Clear. They have 6 steps in assignment because I don't remember if you do need all the 6 steps, but they have the 6 steps in assignment to, I think, not to give you, well, hints on how many steps it should be. And in their problem, it might as well take 6 steps. Because you need to understand that, that for each step in the assignment, they want you to do only one thing. I did multiple things in one square, right? So if I were to go back to the, clear. If I would go back, type, oh, no, not date modified. If I would go back, yeah, so, oh my god. Okay. So, right. Because, you know, in the first cube, you would say, oh, yeah, centroids get assigned random locations. Here's the random points, data that are picked in initial seeds. Yeah. So, the 1 and the 2 are picked as initial seeds, right? And then, well, here, you would basically, the only thing you would do here is color all these points, right? So, like this, these ones would become 1, and these ones would become 2, right? Yeah. This one would become 1, and this one would become 2. And then here, you would compute the centroids again, right? Here, you would reassign those points. Here, you would compute the centroids again, reassign those points. And yeah, so I think here you should stop, and you will basically explain, well, we have now moved the centroids, right, like from here to here, but none of the points actually are now changing their alignment, changing their class, which means that we should stop. Okay, so it's 6 o'clock. We still have 1.5 hours to go. I know it's a lot, guys, but yes, we can now ask questions. But from my experience and from other things, I would think that that Q-learning is very likely to be asked. So I would we'll take a look at that. I would say that they most likely will have something with decision rules and trees, like very likely. Some very minor questions on validation, and most likely something with artificial neural networks, right? Because you need to understand that. Actually, considering they have 2 hours this time, I don't think they would ask this question here. So this question, actually, artificial neural networks, I don't think they would ask, because it really does take a lot of your time to to compute them and to check them. Yeah, can you find the slide and have enough time to apply the formula? Yeah, it's no. The question was whether this question is more about understanding. Well, yeah, you just need to apply the formula, and yeah. The lecture said you wouldn't use Q-learning for multiplayer games, which is during the lecture she said you wouldn't use Q-learning for multiplayer games, which didn't really make sense to me. Okay, so okay, Q-learning. So there might be a couple of ideas, right? Because let's say that we have Q-learning for multiplayer games. Like I'm trying to find like the easiest example. Why it wouldn't be a possible idea. So Q-learning is very good when it's only one player, right? Why is it good? Well, so one of the things that you might have heard is the fact that the problem with the Q table, well, two problems. First of all, the memory problem. The Q table needs to hold all the values for all the possible states and all the possible actions in the state. Let's take Pac-Man multiplayer as an example. Let's say that we have 2 states, right? We have so let's say that we have 2 states. So here we have a Pac-Man, and here we have ghosts, right? And the ghosts are quite far from Pac-Man, right? So now this would have to be a state, right? And then the Pac-Man would have here maybe 4 actions. If he's at a crossroads, I have never really played Pac-Man, so forgive me if this is stupid, but so if he's at the crossroads, you would have two actions, right? Either move left or right. And well, does it really matter where to move? Because well, the ghosts are very far from you, right? But you still need to save this state. You need to generalize it somehow. So, for example, and this is not a multiplayer game. This is just Pac-Man versus the environment. For now, I'm just saying that well, multiplayer games make things more complex. But let's say that now we have the Pac-Man at the exact same position, but we have the ghosts like somewhere here in completely other position, right? It's a completely different state. Like every position of the ghost is its state. So if ghost moves once, then it's a whole different state, right? You can already say that well, if you have one ghost at every single position in the map, it could be like let's say 500 positions, right? Okay. Now we have two ghosts. It's 500 times 500, provided they can overlap themselves. But yeah, it's already a lot. You already well. Just by adding like two ghosts, we're not even considering Pac-Man or his options or map wherever, but we already have like 250,000 different Q value entry tables, and you have to understand that Pac-Man has 4 ghosts, right? So just for 4 ghosts, like I'm making some very small assumptions, but it wouldn't matter too much. We already have this many states, and we haven't even considered the Pac-Man. And so for each one of these states, we then have maybe 4 possible actions. Yeah. You know, like, we can already stop here. Isn't deep Q-learning a form of Q-learning which covers a problem? Yes. But do you know what deep Q-learning actually learns? So there are different possibilities of Q-learning, but you know, so the deep Q-learning actually does not cover the other problem with Q-learning that I wanted to mention. Let's say that we have 6 trillion states like we had with ghosts. Okay, so to make some kind of policy, some kind of good actions, you need to explore a good chunk of them, right? You need to explore some states. With deep Q-learning, what people found is that, well, this exploration of the deep Q-learning, it doesn't have a Q table, it has a Q function. But this exploration of the Q function actually also takes a lot of time. You can see from maybe if you had the backgammon thingy, you could see that deep Q-learning backgammon implementations actually are almost worse than a random agent because they very quickly learn a very bad policy because of reasons that I think are outside of this course. So it actually takes Q-learning a lot less time to converge than deep Q-learning. Because as you said, well, the deep Q-learning needs to learn the approximation of the function while the Q-learning just learns the function. What's the most intuitive way to understand the difference between policy and off policy? Well, policy is, so a policy and off policy, right? So policy is in some way, well, choosing an algorithm, right? So how does, for example, Q-learning, the off-policy algorithm, how does it explore? Well, it takes it is a greedy algorithm. What does the greedy algorithm mean? It wants to maximize its reward, basically, right? So if it has a Q-learning approach, then well, then it might, you know, take. It might be extremely greedy, right? So if it always goes for the best action, then it will always like follow the best possible solution, right? Like so it can take. You know, so for example, let's say that you just use Q-learning, right? And you have not initialized any of the Q tables. You might have like a start here and the end here, right? And you don't know any Q-learning tables, so your agent actually just randomly thinks, hey, what if I, you know, I just randomly choose the action which made me go this way, right? But there's a better action which goes here, right? And because the algorithm is greedy and always wants to maximize its reward, because it found this path first, it will never actually find this path first. So how does Q-learning solve it? Well, one of the solutions was to simply like take the best action And in some cases, with a very low probability, with a probability that gets lower and lower the more you explore, you just take take a random action, to make it more explorative. With an on policy, you actually have some policy for choosing an action. So let's say that that we have a very simple on policy approach would be in chess, right? Let's say that we just take some random actions in chess, but our only policy is if we can do a checkmate in one turn, then we always do it. Right? That would be, for example, a policy. That would be a predetermined idea of how to follow it. A Sarsa basically creates a policy. It doesn't maximize its rewards. It creates a policy of when to do what. Yeah. I'm just gonna check if this corresponds with my notes. Yeah. So according to some policy, right? But yeah, for Q-learning, we just always take the max action, unless we have some random thing. Yeah, that makes sense. Did you guys also have TD lambda as your reinforcement learning algorithm? Nope. Okay. Then I will not explain it. Yes, Sarsa is the on policy method. Because Sarsa actually, it looks at the state, and Sarsa chooses an action, right? So it's very different. Not even TD0, I think. Okay, yeah. So Sarsa actually, yeah, as I said, Sarsa looks at the state, and then according to some function chooses the best action. The Q-learning doesn't care. It just chooses the best Q value, basically. So you still have some idea, right? The Q-learning is just greedy. It just wants like the most reward that it could possibly have. Yeah, and well, for example, for multiplayer games, like deep Q-learning can be a problem, Lars, because of the curse of dimensionality. The table size or the dimension of the function increases exponentially. So it actually takes longer and longer to estimate. For example, even backgammon you cannot put into a Q table. So yeah, for multiplayer games, because let's say that you have something like, a very complex one, League of Legends, right? If you would, so let's say that you don't know, the positions of the enemies. Well, that not knowing the positions of all 5 enemies at the beginning of the game would be one state. Not knowing the positions of 4 out of 5 enemies would be like a second state. Not knowing 3, it basically gets a lot more and more complicated, and you just like run out of memory space. So you have like some crazy tables which have more entries than the number of atoms in the universe. Okay, let's see what you guys got. Okay, what's your topics? Any questions about recommender systems? How far did you go into those? Just gonna check really quickly. The INN, yes, I refuse to apply the algorithm to the thing. Like I can do it, but I will also have to look up this algorithm because I don't know it by heart. But I think like it's just like I know it by heart. Like I know it's just like a linear sum of the features activated by sigmoid. But I will make a mistake most likely somewhere. Okay, well we can do it, sure. Okay, so let me see. Okay, I need to remember what those ones and zeros look, because one of them stands for layer, the other one stands for the node in the layer. Okay, yeah, cool. So this one is the layer, and the other one is the node. Okay, cool. Yeah. So because we have three inputs. Yeah. Okay. So what do we have? We have x1, x2, output a1. Sorry, output a1, 2. Okay. Well. Yeah. All right. Okay. Cool. Yeah. So let's do it. Yes. Okay. So output a1, 2. Okay. I was confused about this one, but it just means this one. Okay. Cool. Yeah. Right. So output a1, 2. What are we gonna get? I'm just gonna make it smaller, guys, to be able to write on it. Annotate. Okay. Yeah. All right. So a12, right? So it's a it's linear sum activated by a sigmoid, and for every input we have a certain weight. How can I do it the best? I don't want to write it. Notepads. Okay. We're just gonna have a simple notepad thingy here. Okay. So what we're gonna have here is yeah. So yeah. Okay. Cool. So the first input that we get from the input layer is the bias unit, and we can see here that the weight of the bias unit for the node A is 0.5, right? So we get 1 from the input layer, which is 1 times 0.5, right? Times its weight, plus x1 is for now 0, plus 0 times 0.3 here, plus 0 times minus 0.3 there, right? Okay. And then what we get is, well, simply 0.5, right? And then we activate this 0.5 according to the sigma. Do we actually activate it? Oh wait. Okay. Yeah. Okay. Yeah. Cool. Yeah. So then we activate it by sigmoid, and we can see that if our x, which is right now 0.5, if it is 0.5, then we have a 1. So this would get a 1. I'm like 99% sure. This would get a 1. Right? Then the output of A2 would be the same, but it has the minus 0.1, right? So because the input, the x1 and x2 did not change, they're both zeros. We only need to, in the first case, to consider the bias unit. So the unactivated A2 output would simply be minus 0.3 because minus 0.1 because it is the weight of the bias unit, and the bias unit is the only one. Shouldn't be both q times 1 be minus 3? Yeah, yeah, like this is okay. All right, sure. Let's just treat it as it's a minus. Fine. Okay, yeah, but then our equation still doesn't change because we still have zeros for those inputs, so their weights don't change. So then this would be like A1, 2 is this thing. Then we want to do the A2, 2. And so the A22 is this one, and so it gets, well, the same thing. It gets the bias node, then it multiplies it by minus 0.1, plus 0 times 0.3 plus 0 times 0.3. Okay. Oh, that's not what I wanted. 0.3. Okay. And well, the answer is very simple, guys. What is it? It is minus 0.1 because the rest is 0. So we can see that minus 0.1 is 0.17. So then this one would be 0, oh, 0, oh yeah, okay, yeah, good catch, 0.17, okay, cool, 0.17, yes, sum of theta. Wait, sum of theta 2. Oh, I think they mean this one. Okay, wait, yeah, I know mind. Yeah, they mean this one. Yeah, yeah. Okay. Right, so then we have the A1. I'm gonna do it on new line. A13 is, okay, so we get the bias unit as not here, so the bias unit doesn't change, it always gives 1. It's gonna be 1 times okay, yeah, cool. So 1 times minus 0.3 plus 0.2, oh, plus, yeah, plus, right, yeah, okay. So this one outputs 1, oh Jesus, they moved, times 0.2 plus 0.17 times 0.17 times 0.2, right? Yes, 0.2, not minus 0.2. Okay, and we get some value. Jesus, okay. I would appreciate it if somebody could calculate this value in their phone and then give it to me. No, but I'm gonna calculate it on my phone. It's fine. I've slept for like 3 hours, so because I will not continue this line of thought. Yep. Okay, so we let's see if I made any mistakes. Okay, so we get minus. Okay, I have to make it even bigger now. Minus 0.066. Was it correct, or should we not have activated it? I don't, because it could be both. I think like it should be activated. Yeah. Yeah. Okay. Well, minus 0.06. Because they explicitly have like, well, it should be activated, right? Because it's a Z and then A1. I don't remember how they gave it to you, so I'm just gonna look it up. Because usually those things are activated. So I'm just gonna check if I'm doing everything right. Yeah, sure. Input weights transfer function and input activation function. Oh, so yeah, okay, so they didn't activate it. Okay, I would activate it, but you know, that's just me. Because it was also not, no, oh well. Yeah. Yeah, so they didn't activate it. Just gonna check if I'm correct. Yeah, wait, so what should XOR output for 0, 0? Yeah, okay, it is activated. Okay, yeah, cool. So the XOR should output for 0, 0. I don't even remember that. XOR 0, 0. Just gonna very quickly look it up because I think it's 0, but I'm just. Yeah, for 0, 0, we will output 0. Okay, yeah, cool. So with an activate, yeah, so we need to activate the function every step. Yeah, okay. So we get here minus 0.06. Annotate minus 0.066. Okay, 66. Okay, whatever. And then we activate it, and then we get 0, basically. Okay. So for the next one, we do the same exact calculations, except now the x2 becomes. Give me a second. Now the x2 becomes 1. So what does it mean? Is that in our equation, we would make this 0 a 1, and we would make. Yeah. Okay. Cool. We would make this and this 0 1 because they correspond to the x2. The rest of the things stay unchanged, and we're gonna have 0.5 minus 0.3, so 0.2, and activated it's gonna be 96. Whew, okay. 0.96. Yeah. Oh, really? Oh yeah, okay, yeah, that's true, because they both become 0.2. Okay, yeah, 0.96. This one also becomes 0.2 because this one becomes 1, and minus 1 plus 0.3 is minus 0.1 plus 0.3 is 0.2, not minus 0.2. Yeah, which gives us 96. So then we just so the bias stays unchanged for this node. Then we remove this one with 90.6, 6, and this one is 96. Oh boy. Okay. Yeah, I mean, sure. Yeah, so just one. I mean, but we need to put a sum here. So yeah, but basically you activate the sum of every node, and then you input into the next one, and yeah, the bias node just never changes. Yeah, but like. Now imagine that you will have to do the whole table in the thing. It's fun. Yes. Some, yeah, but you know, we know that it's like one activated, so it's just wherever. And this one is, I'm just gonna cheat here and make a prediction. It's gonna be 1, 1. Yeah, 0. Okay. Yes, perfect. My prediction was a bit wrong. Okay, so yeah, 615. Yeah, so we you just need to activate every layer, basically. Which is not always the case because sometimes you might want to use non-linear. Sometimes you might not want to use activations. Hmm? So that they can give you more points when they see where you fail. So like if you because you know like it's a XOR problem, so they cannot just give you points for like 0, 1, 1, 0. So they actually are looking more for these things. That's how they explained it last time. Yes, this is easy points, but yes, it is very time consuming. Okay, so we still have 23 participants have survived this far. Hey, Natasha, you came. Okay, so are we allowed to have a calculator at this exam? Yeah, I am not a TA, guys. I have no idea. But having said that, yes, you do. I think. But do not quote me on this. Okay, yeah, I hear that on the session on Wednesday it was said that yes. But yeah, of course, you would not calculate like something like this by hand. You know? And also, so for KNN, while you do need to calculate the center of centroids, you don't get the x and y axis, so you can just like put them where you think they might be. Like not too far, but you can see like where they might be. And print copies of everything. Not everything, but only the study materials. So you can't just print out the exams, I think, because I've heard something about that. They're putting limitations either this year or the next year. And the question is like, how do the old people know? And the answer is, I'm not omniscient. I do not know. But I'm just saying, your notes sound pretty open to me. Yeah, like, I don't know. Like I've heard from some student representative that they're wanting to change it. Can you think of possible questions? Natasha, is this related to the... I'm going to just very quickly remove it. Is this related to the question with the customers? Or... No, okay. So what... Can you think of possible questions regarding linear logistic regression? Where do you use one and where do you use the other? I think it was 6 or 7. 6, artificial neural network, and 7 was also artificial neural network. Oh no, it was just in the mock exam that they provided. No, they provide a mock exam with reinforcement. Actually, one of our assignments was reinforcement learning, I think. No, it doesn't mean. Yeah. But yes, basically, like they love to ask very bad questions about decision trees, especially. For example, on the receipt last year, there was a question like this, right? Actually, you were given decision rules. And I was actually very concerned about this question because they said, okay, from these decision rules, make the smallest possible tree. And you had 2 decision rules, I think, which I don't know if you had 2 decision rules or you only had 2 decision rules that mattered. So if you only have 2 decision rules that matter, what is the smallest possible tree, guys? So basically, if A and B, then plus. If neither of those, then minus. What would be the best? Well, so the answer is, I'm gonna go into the lecture for the decision trees. Was it decision rules, the same trees? I think so, yeah. Okay. So, there's a very interesting term for it that I already forgot. But if I can just very quickly... No, it's not here. It's only rules. You lied to me, guys. Oh, wait, no, it's here. Okay. No, what? I think it was somewhere here, somewhere else. Wait, validation, instance-based learning? What is BL? Oh, okay, cool. Lecture 2, oh yeah, decision trees, okay, yeah, because why would you spell it out? Okay, so cool. Right, so actually, I don't remember the name of the tree, but you also needed to name the tree. Okay, I can't find it, but it was like something with an O, like, so the trees that could contain 2 or more rules in one branch, which was like oblique trees, yes, okay. So the answer was just oblique trees. So the answer, they gave you a whole A4 paper to write your decision trees, like based on those rules that they gave you, and it was like 1 block. Yeah, they like doing it, so be careful. Don't trust anything, please. Because I was like, this can't be true, right? And no, it was true. So I was correct. Yeah, it's probably mentioned somewhere here, like oblique. Yeah. Okay. Cool. Public decisions. Taking my multiple attributes. Yeah, that's like the smallest possible thing. Yeah. So basically, let's say that you have a plus, you have a positive example when both A and B are true, but in any other case you have a negative example. So so basically, so you have an AND gate. So an AND gate could be just yeah at the same time. Yeah. So in this case, like x plus y is smaller than 1. If it's true, then you get a plus. If it's false, then you get a then you get a false. I don't know. Yeah, so you get a red if it's less than 1, and if it's bigger than 1, then you get a plus. Yeah. So theoretically, like x could be could be like 2, and then the y could be like minus 1.5, and then you would still like be. Yeah, I mean it could be possible. It could be possible. Bruh, yeah, indeed. So this is the kind of questions that you can expect, that are completely easy and useless because you need to just remember that there was one decision tree that you will never use. That was interesting. Okay. Yeah, but so far I think it went well. Like the mock exam was quite easy, and actually the real exam is probably easier than this because it's only 2 hours. So they can't ask artificial intelligence, because that's like the only question that they can ask. I mean, not artificial intelligence, the fully connected neural networks. I meant. Yeah. Hmm? They most likely won't ask you to do something like this, because well, it just takes way too much time. So they'd rather because like this would take at least half an hour, So not like this way of examining. Nobody likes this way of examining. What you should be examined on in machine learning is on creating some project or like solving some issue or whatever, But yeah. Hmm. Yeah, yeah, I know. It doesn't make sense. Andre, can you also explain why we're not including rule for B in the two question? Rule for B. Okay. So yeah, for B, well, because for B, for A and B, it basically doesn't matter because they all like the B either leads to C or it leads to a plus. But like so if B is bigger than 20, then it's a true. But if it's smaller than 20, then let's see. Wait. I knew it. From A I get it doesn't matter. Yeah, okay. Wait, let me see. Because I knew like this thing had only 2 examples, but I thought it was B and C actually. B and D. I think whoever like suggested the issue like actually made me confused because in my answers like I had B and D I think because like if B is bigger than 20, let's say that the only thing that we know is B is bigger than 20 is that well this doesn't matter. This might be, but the D is the other one that decides everything because it's either the B decides or the D decides because the D here does not get to decide, so the B decides. So I think B is bigger than 20 and D smaller than 10 is the answer. Yeah, because that's what I came up with when I wasn't half dead. Yeah, it's B20 and it's B bigger than 20 and it's D smaller than 10. Because like let's say that that we go into paths here, like A doesn't matter. If B is bigger than 20, then we already have a plus, and if B is not bigger than 20 or like wherever A, then D decides. So B and D are the only ones that decide actually. So let's say that A is smaller than 30 and B is bigger than 20, then we get already a plus, right? So let's say that we have like an example like yeah, I mean this is not a good question to answer, but let's say that A is 20, B is 30, and D is 5, right? So okay, let's see what we're gonna get. So we're gonna get already plus here, right? Because we're just gonna go like immediately through this path, and we get a plus. We get a positive example. If we now say that A is bigger than 30, so it's 40, then D decides, basically. Yeah. Mm-hmm. Yeah. C. Actually, yeah. Hmm. Because B20. So let's say that. Yeah. Get going. But thanks for organization. It was very helpful. Okay. Thank you, Lars. So yeah. Yeah. This is a very confusing thingy. Because I don't even know how to actually solve it very easily. And I'm working on my original research in machine learning. Okay, so the A never matters. We decide that, but D does matter, right? So we have D and we don't have A. What if we know C? Well, C doesn't matter because C doesn't. Okay, let's try to actually write down those rules. Have a good evening, Lars. Here. Even I'm struggling. Okay. If you probably like created a decision tree like this for you by yourself and ask the teacher to do it, like he would also have a problem. So that's fine. Okay. So if a 30, well, the A doesn't matter, so we can just say if B is bigger than 20, then plus. If C is bigger than 20, then plus. If D is smaller than 10, then minus. Then minus, yeah. Wait. So how can we cut off? Yeah, okay, no, actually, yeah, this is correct. Like the C and the D should be, yeah, okay, yeah. No, so yeah, the D and the C actually, yeah, the ones I decided, because the C will always, like, it's always going to be a positive example unless C cuts off D and D can't decide, because C always goes to plus. So basically, like, you would want to go to D because D is actually the one who decides, and the only thing that could cut off D is C in this case. Well, do you care what B is? Because if B is, so B can have two paths. It either has a positive example or it goes to C, which then decides. So it actually doesn't matter because everywhere else you get a positive example. So like you don't care what happens basically like in here, right? In this part of the thing. Wait. You don't care what happens what happens here, because whatever happens here ends up in a plus, right? So then the only other way it could end up in a plus, if a C is bigger than 20, then it ends up in a plus. If C is not bigger than 20, then D decides. But basically, D decides what is positive and what is negative unless it gets cut off by C. And so, so right now we have like a thing, right, where C, yeah.
If there's like something where it goes through C and D and becomes negative, then you can cut it off because C, if B is 30, it won't get to C.
Yes. If B is 30, and then we get a positive rule.
Yeah, yes, but then they're never gonna let D decide, so it means you can't go through. So if we had like C is 30 and then D is 5, if we just let C and D decide, that would be negative, but B can make it positive.
hmm. Yeah. I never received the answers to that question, so yeah. Okay, yeah. Wait. No, so it doesn't matter. B. Yeah, so if C is smaller than 20, but B is, yeah. For decision list, what is the rules that corresponds to decision tree given below? Hmm. Then you have a problem that like B can never be reached because you need to have an ordered set of rules, right? And we know that, well, A kind of doesn't matter. So B, would need to basically start with A if we wanted to go to B, right? Because it doesn't cover the whole tree, only the left side of it. And then you would basically have every single condition in there, like if A, then B, then C. So I think that the correct answer is C and D. Hopefully they will not ask it, but yes, because the other question with like oblique trees was even easier than this. Yeah, so it's just, yeah. Because it's the logic that you will use that will bring either your success or downfall in this case. Because yeah, if you have the ordered set of rules, then B is not always gonna be like used, basically. Oh well. Okay. Any other questions? Let's see what you guys had. Annotate, clear. So yeah. The not SVMs, the recommender systems you guys understand? Okay, cool. Decision rules, the instance-based learning. The Bayesian learning, I'm afraid I will not be able to explain too well. I don't even remember what it was. Okay, yeah, that's fine. The distances, that's fine. Okay. Let me just quickly see what Bayesian learning is. Okay, yeah, sure. Oh yeah, okay. They might very well ask a question on this to explain the planes of, to explain the hyperspaces. So be ready for that. This hyperspace of the Bayesian learning is definitely the hyperspace, the hyperplanes, definitely like something that they would be able to ask you. That is very likely to be the case, actually. So yeah, I would just learn this example because you might get a picture like this and have to classify it because it doesn't take too much time if you know what you're doing. So they might very well ask it. Not easily. I knew it a year ago, but I'm more into computer vision, so I don't know every part of it. For instance, x class y. Mm-hmm. Mm-hmm. No, I would not be able to explain it actually. No. You have a recorded lecture, so I would. They don't disappear. Yes, because they are sorted by recent things. So if you actually go to here, you actually need to choose the. So I'm gonna help somebody physically on the internet while keeping safe distance. So yeah. Okay, guys. So for people who don't know, you can actually find the old recordings. They don't disappear. To be skin base. Yes. Is it also new information for you or? Why? Okay, I'm gonna send it to all the Bachelor chats right now. How to find those recordings when I come home? Okay, so it's fine. Yes, it is very. Why do they not explain it to you? Like, hey guys, this is our Corona things. Yeah, no, it's fine. Yeah, it's weird. I actually didn't know that either, so I used to download all of the videos, and I was like, oh, that's. Are you guys here for the?
We're just wondering where's Bella?
Okay.
Can we stay here to do like the assignment?
To do that?
I don't know if you're working on the lab 6.
No, no, you can stay here. We are going through the exam questions. We already went through through the mock exam, basically.
But the building is not closing.
The building is closed. I fixed it, so the building is closing at 7:30. Yes. The power of a person who does stuff is. Okay. So we're switching to Russian, huh, Natasha? Um, um, okay. Oh yeah, you. Okay. Right. This one's graduate. This one's. Yeah, Natasha, I will answer you tomorrow. I will just solve it myself, and then with the main people on campus. They, it is going well. Okay. Yeah, Natasha, I'm gonna tell you the thingy tomorrow. Okay. I'll just send the yeah, I'll send you the solution for the exam because right now it's too late to look at those things. There are. Mm. Yeah. But hey, you always learn something new. You know, today you learned that the lectures do not disappear after a while. That's fine.
For question 8,
Give me a second. What was question 8?
starts with the gradient descent.
Yeah. Okay. Mm-hmm.
Yeah, the slides are wrong.
Yes, the slides are wrong.
Okay. And I understand that the step size decrease when it gets closer to
Mhm.
11 and a half, but then is it behind the explanation of it?
Well, you have to give a mathematical explanation.
And
Do you remember in wait. Do you remember in which slide lecture there was a gradient descent? I think in yeah, in last one. Yeah. Okay. So the slides yeah, so slides contain. So the question was why the slides are wrong. The slides contain this exact image of the gradient descent, which is not how it works because you can see that the step size between the x's does not change, and it should get smaller and smaller the closer you approach. Yeah. So gradient descent. Okay. Cool. Give me the algorithm, please. Yeah. So the gradient descent. Yeah. So the gradient descent step is defined by this equation, right? So the previous position minus learning rate times the first derivative times Jacobian matrix, but this doesn't matter. So the first derivative, the closer you get to the minimum, the smaller the first derivative becomes, right? Because the first derivative is how fast it changes, right? But like the closer you get to the minimum, the slower it usually changes. Yeah. Of course, you know, if you are on a plateau, like the first derivative, the gradient descent will have a lot of trouble with it. Yeah, yeah, yeah. That's because it has it has some effect on the step size. So yeah, so if you would just say, yeah, okay, so you would just write this equation. You would say, okay, so the first derivative actually becomes smaller. Then it would be fine. Okay. Mm, okay. I'm gonna stop the recording for now, though. Like, oh, actually, no, I'll just keep it going because why not? The question 9, right? Yeah, explain your words purpose. Okay, so what don't you understand? Mm-hmm. Yeah. So basically, slack variables mean, okay, so our data might not be linearly separable, but what if it was? It is very, I mean, it works, but it is very stupid simile concept because you just, well, the numbers, so the examples that do not make the data linearly separable, you just simply move them, basically. Yes.
Because in the slides they do something different. Like they create a margin
Mm-hmm.
and
Yeah.
yeah, they say that we can allow some misclassified
Mm-hmm. Yes, because well, they move them. So they move them and then they consider them. That's way. So because they move the. So I'm just gonna take the slides because it's easier. It's SVMs. Yeah. Slack. Okay. Yes. Oh, okay. That's already not good. Okay. Yeah. So yeah, we have calculated. Basically, let's say that we have this data, right?
here we can separate it linearly.
Yes, it's a bad example. It would be a lot. It would be a lot better if, like, yeah, basically we can basically move this plus to here, and then we would basically be having like a better margin. Like if we would just, just move the. So if we have like kind of a line here, right? That like that is the closest line to the positive examples. We could just use the slack variable to move all the other examples to that line, and then we create the widest margin by that. So basically, if we have a problem with creating the widest margin, then if one data point creates a problem of creating the widest margin, we just don't consider that data point. Basically, I mean we do consider it, but we move it by using slack variable.
It's the slack variable that moves it.
Yeah. So you can see that it's an equation, right? So this is the equation that describes well yeah. So with this equation, we actually describe we minimize the maximum margin, right? We take the normal of the vector, and then yeah, well, we for every data point for which we have a slack variable, we sum this slack variable by some weight, and then we basically move all of the points that we don't like. So the slack variables are only created for points that we do not like.
Okay,
By
and
moving
why do we move them?
we move them to the I think to the closest to the minimal margin of positive examples, for example. So you can see that this line here is very close to pluses. So we just move it like as close as possible to that line. We have some questions. Any tips on what to bring to the exam in terms of notes, formulas? That's quick. Yeah. So please do yourself a favor and print out all the slides at 6 slides per page, because there will be probably questions, like obsolete decision trees, the one that I discussed earlier, and you would need to to actually look at the data, to look at the slides, and to remember what you have to use. The summary that you have from Incognito website cannot cover nearly everything. Read my paper. Yep. I mean, at 6 slides per page, it's not as bad. But yes, you don't use like 90% of those things, if not 99. But it's always better to to print out 100 more pages than to miss a question because the answer to it was on a very specific slide that you just didn't bother summarizing. Yeah. There was one question about an artificial neural network that was worth 10 or 15 points, and it was only one. It was only about one concept at the very bottom of one slide, so really print the notes. Yeah.
Hello?
Hi.
How long do you
Yeah, we had until 7:30, but we can like
past 7?
yeah, we can wrap up.
Building in about 20 minutes.
Okay, sure. Yeah, we'll start going in like 10. Okay.
All right, it's
Alright.
fine.
All right. Perfect. Thank you. Yes. Okay. So hopefully you guys learned something during this lecture. And hopefully you're all gonna pass for the exam with high grades, with a 10 out of 10. Maybe. No. Okay. Natasha, are you going to pass with 10 out of 10? Can you promise me? Oh, okay. All right then. Okay. No promises then. Choo, 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 choo. Yep. Yes.
You do question 7?
I don't know. Let me check.
Because I never did.
Yes, we did do it. Okay.
And I was just watching the video.
Yeah, we did do it. And like we have. Wait, if I just. This is the for decision rules, and I can't. Okay, whatever.
Why do we need all of these?
No, I was just doing an example, so it's not.
So for this one, we just need one rule so that if d smaller than
I don't really know. I'm not that good in decision trees, but I think you need 2 rules, maybe. But I don't remember. Like I know you don't need A, but like it's complicated.
because of d, we know that if it's smaller than 10, it's always negative.
Mm-hmm.
And can we just say that if it's smaller than 10, then it's false?
Well, yeah, but the D could be blocked by C, for example. So like if C is bigger than 20, it doesn't matter what D is, because it could already be blocked. So D could be like like 20, and C could be 30, and it would still be true, still be positive. No problem. What was the channel called again? I will send it to the name of the channel. I will send it tomorrow morning to the to all the not to all the to the bachelor group. Okay, see you. Make sure to subscribe and like all our videos. The next upload is in early February. About neurosampling, guys. I'm gonna spoil it a bit for you. I'm gonna actually stop the recording.